In Chapter 6, we learn 5 different methods to solve for area and volume. The first method is disk or washer method, which we use to solve for volume. The second is cylindrical or shell method, which we also use to solve for volume. The third method is Pappus theorem, which we also use to solve for volume. The fourth method is cross-section, which we also use to solve for volume. And the fifth method is double integral, which we can use to solve for both area and volume.
How to find the volume using disk and washer method. So in order to find the volume by using disk and washer, we need to use few simple steps. So step number 1. Take a segment to axis of rotation. Take a segment perpendicular to axis of rotation. So for example, we'll have x-axis, so y-axis, x-axis. Our axis of rotation will be around x-axis. So we will take a segment. So for example, we'll have a curve y equals square root of x. We want to rotate around x-axis, so we take a segment perpendicular to x-axis. Okay, step number 2. Find the endpoints. The endpoints. So in order to find the endpoints, we take the same segment and we'll find our endpoints. So the bottom endpoint will be some x value and 0 since it's on the x-axis. And our top point will be some x value to the curve, which is square root of x. Okay, step number 3. Find volume of a disk. So when we're rotating around the x-axis, we get a shape look like this, and when we rotate our segment, we get a disk with a thickness dx. So when we get the disk, we need to find the volume. Find volume, which will be dv equals 2 pi r squared dx. Okay? And step number 4. Evaluate the integral. So evaluate. Our volume will be equal to integral from some point A to B. So let's say we're going from 0, for example, to our point B. Let's say it will be 2, for example. So from 0 to 2, pi r squared dx. In order to find our r squared, we will use our endpoints, so it will be our square root of x squared. And therefore we'll have volume equals to our integral from 0 to 2 pi x dx. And we already learned in chapter 5 how to solve this kind of integral. Okay, now that we covered 4 simple steps, we can go to an example. So example 1, we'll have a curve. This is our y, x. The curve, which equation is y equals sine x. So we need to find the volume from 0 to pi, rotating around x-axis. So first step, take a segment. We will take a segment from here to here. Our circle with a thickness dx. Okay, step number 2, segment points. The bottom ones will be x, some x value to 0 because it's on the x-axis, and our top point will be x sine x because it touches the sine curve. Step number 3, find dv, which equals to pi r squared dx, which equal to pi, our r is equals to sine x squared dx. And then we take this equation and integrate it. For the step number 4, our volume is equals to integration from 0 to pi, pi sine squared x dx. And we know that the pi is constant, so we can take it out and we just integrate sine 2 of x by using half-angle identities, which we learned in chapter 5. Okay, so that was the example of a disk method. However, in the disk method, we can notice that when we take a segment, we get a circle, a complete circle with no holes or anything in it. However, what happens if I take a segment and it will look like a donut? So we'll have a hole in the middle. So let's look at the example of, by using the same exact steps, let's look at the example of a washer method. So we'll have again our y and x. We'll take the same sine curve, y equals sine x. However, now we also will use the x curve, y equals, cosine x, sorry. And we want to find this volume over here between the two curves. So of course we want to find from 0 to this intersection here. In order to find this intersection point, we put cosine x equals to sine x, and we find that this intersection is pi over 4. Okay, so when we take our segment, here and the second segment here, we find out that we get, when we rotate around x-axis, we get a circle over here and then a bigger circle down below. So we get a donut looking shape. So here go, let me draw it on the side. So this donut with the thickness dx, both of them has the thickness dx. So for the step number 2, we have to take segments. When we take a segment, the first one will be again some x to the sine x, because that's our first curve. The second will be x to our second curve, cosine x. Okay, so we go from x sine x to x cosine x, because we have two heights. Okay, step number 3. Our dv is equals to pi r squared dx. However, this time, since we have two circles, a donut, we're going to go make it pi big R, which is the radius of a bigger circle, squared, minus pi little r, which is the radius of a smaller circle, squared dx. When we plug in for big R, that will be our cosine x squared, and for little r, it will be our sine x squared, because our smaller circle reaches to only the sine curve and our bigger circle reaches to the cosine curve. Okay, so step number 4. Our volume is equal to 0 to pi over 4, as we already found the intersection point, pi, and then cosine squared x minus sine squared x dx. And again, we can take pi outside since it's a constant, and solve for cosine squared minus sine squared, separate into two integrals, and solve from there with a double angle formula like we learned in chapter 5.
Hi guys, I'm going to explain how to use the shell method in order to find volume of a function that is being rotated around an axis. Now the shell method is very similar to the disk method with only a slight few changes. Now first of all, just like the disk method, we will choose a segment. That's our first step. Now, unlike the disk method, the segment that we're choosing will be parallel to the axis of rotation. So for this example that we have the equation y equals 1 minus x squared, and we're going to choose to rotate it around the y-axis. So we need to choose a segment that is parallel to the y-axis. So here, this can be our segment. Now, our next step, just like the disk method, we are going to find endpoints. Now, the endpoints of our segment right here, let's label them. The top endpoints will be x, because it's x away, and the y value will be 1 minus x squared, coming from the equation that we have. We're going to keep it in terms of x. Now, the bottom endpoint, the x value is also x, and the y value is 0. So, still very similar to the disk method. Now, here's where it changes. Now here, we are also going to find dv, but the equation is different. When we take this segment and rotate it around the y-axis, we are going to get a cylinder, or a cylindrical shell, with thickness that is dx. So when we have lots of these cylinders, it's going to create the shape, the volume that we're looking for. Now, this segment being rotated around the cylinder, if I take that cylinder and stretch it out to a rectangle, we have this. We have our segment right here, which is of height, well, let's put the endpoints right here, x and 1 minus x squared. So the height of this segment will be 1 minus x squared, as you can see by the endpoints. And the distance, since it's a circle, it's going to be 2 pi radius. Okay, so our radius of this circle, as we can see from the diagram, is our x. So the equation that this gives us for the surface area of a cylinder that is created by rotating a single segment becomes 2 pi r h dx. So our h will be the 1 minus x squared that we get from our endpoints, 1 minus x squared, and our r will be our x. So specific to this problem, this will be 2 pi x 1 minus x squared dx. Cool. And finally, for our fourth step, we need to integrate this so that we account for all of the shells that can be created while going down the function. So we'll do the plane equals the integral of 2 pi, in general form would be r h dx. In this case, it'll become volume equals 2 pi x, which is our radius, and for h, 1 minus x squared dx. And in this equation of the graph, this is of y equals 1 minus x squared. Our endpoints are going to be 0 to 1. So we are integrating from 0 to 1. Now, to integrate this is very simple. We pull out the constants. So now we have 2 pi 0 to 1 of x times 1 minus x squared dx. And then, now just to review, we had the shell method, and the steps are to choose a segment. We chose a segment that is parallel to the axis of rotation. We find the endpoints. The endpoints are in terms of x, because the segment that we have goes down the function from 0 to x. If we were rotating around the x-axis and had a segment like this going across like this, which would be parallel, we would have to go from y, 0 to 1 or 1 to 0, whichever way, and then everything would be in terms of y. Our main equation for this, for the single segment being rotated around, will be dv equals 2 pi rh dx, where r is the radius of the cylindrical shell that we're creating, which is usually our x, and the height is created by the endpoints. And then we take the whole thing and we integrate it to get the volume. So I went ahead and I did all the integration, and I will walk you through it. So we left off at 2 pi, the integral from 0 to 1 of x times 1 minus x squared. I distributed the x, and now we have x minus x to the third from 0 to 1 and multiplied by 2 pi. Take the integral of it, so now we have 1/2 x squared minus 1/4 x to the fourth from 0 to 1 multiplied by 2 pi. You plug in 1 and you end up with 1/2 minus 1/4 and 0. When you plug it in, you get nothing. So you're left with 2 pi times the quantity of 1/2 minus 1/4, which equals 2 pi over 4, which simplifies to pi over 2. This is the volume that we were looking for when we rotated the equation y equals 1 minus x squared from 0 to 1 around the y-axis. Now what happens if we have a shape like this square, and we are asked to find the volume when you rotate it around the axis of y equals x? Now this is difficult because with cylinder and shells and disk method, it's hard unless we rotate the entire xy axis 45 degrees, so that becomes aligned with the y equals x line. Since that's so difficult to do, we'd rather use another method called Pappus theorem. Now Pappus theorem is very simple, and what it says is it takes all the points, every value in here, and puts it all together as 1. And that is the center of mass. And we take that 1 point and we rotate that around the axis of rotation. And since that 1 point represents the entire area of that shape, we will get the volume of the entire shape being rotated around the axis. This is a very easy formula. Pappus theorem is volume of the rotated shape is equal to 2 pi d, which represents the circumference of the circle, and d represents the radius of rotation. This radius of rotation is a line that is perpendicular to the axis of symmetry, axis of rotation, and it starts from the center of mass. And we multiply all of that by the area. This is the area of the shape. So let's try this problem. We have a square that has sides of 1 and is located here, and we want to rotate this. So first of all, we want to find out the area. The area of a square with sides of 1 is very easy. 1 times 1 equals 1. So area equals 1. Now we need to find out the radius of rotation. So let's enlarge this square so that we can see it clearly. And this is going to be our axis of rotation with y equals x. And we know that the center point is going to be over there, the center of mass in a square. And this is given because half across of the x, which is 0 to 1, will become 1/2. And halfway up the y, which is 1 to 2, will become 3/2. So this is the coordinates of the center of mass. Now, in a square, we know that if you divide it, this becomes a 45-degree angle. And this is also a 45-degree angle. And with 45, 45, 90 triangles, we know that the distance across is root 2 times the sides. Now, since the sides are 1, the distance across is root 2. And the radius of rotation that we're looking for, which is just half of the diagonal, is going to be, which is d, it's going to be root 2 over 2, half of the diagonal. So now we know the area and we know the radius of rotation. And now we can plug this into our formula and we will get volume equals 2 pi times our radius of rotation, which is d, which is root 2 over 2, times the area, which is 1. And this gives us, simplified, to root 2 times pi. This is a very simple method of Pappus theorem.
Okay, so a different type of method to find the volume of a 3D shape is called cross-section. So once again, we'll have to have a few simple steps in order to solve this kind of problem. So step number 1. First, we need to draw a picture. So we'll have something describing what's going on in the problem. So we'll have to draw a picture to help us find what we're looking for. Step number 2. Since we're in Calculus 1b, we'll have to take a segment. So take a segment. This segment will be a cross-section of whatever it is. Let me write the steps first and then I will give you an example. So step number 3. Find the area of the segment. Find the area of the segment. Okay, and step number 4. Evaluate the integral. So evaluate the volume as integral from a to b, our area a of x, and thickness d of x. Okay, so 4 steps to follow. So let's look at the example. Let me keep the steps in here. Okay, so example, volume of the graph is x equals y squared with the, so graph is equals x equals y squared with a triangular cross section. So we'll have a cross section as a triangle where our height is h equals 1 over 4 and the base is from y equals 0 to y equals 3. So since we have given the base in terms of y's, we have to transform our equation in terms of y. So we'll have y equals square root of x. Okay, so here let's draw our graph. So it will be x-axis, our y-axis. This is our y equals square root of x, and we're looking for the triangle cross section. So the cross section will be something here, which when we cut will look like a triangle. Okay. So step number 1, draw a picture. We drew a picture. Step number 2, take a segment, and our segment will be from some x value because it's on the x-axis to negative square root of x, to again some x but on the other side, so a positive square root of x. Okay, so step number 3 will be to find the area. Find the area of the segment. So our area will be equal to 1/2 2 root x times 1/2 root x which will be equal to 1/2 x. So where did I get all this 1/2, 2, and root x? So this segment, this part from here to here, from here to here, will be our root x, right? So this part is the same thing, root x. When we combine the two, this whole length will be 2 root x. Okay, so that's where I got my 2 root x. This is the area of the triangle, 1/2 base times height. So base is 2 root x. And so will be our height, root x. Okay, y equals root x, that's our height. Okay. Step number 4, evaluate our v, which will be equal to our integral from a to b, we'll figure out in a moment, 1/2 x, which will be our area, dx. So a to b, of course we start at 0, so we will start our integral at 0, and the height of our whole segment is x equals 9. X equals 9 because we're given from y equals 0 to y equals 3, but because we're transform it in terms of x, we plug in 3 times 3 is 9. Okay, so we go from 0 to 9, and this is easy to evaluate. We print 1/2 in the front and we get 1/2 times 1/2 x squared, which will be 1/4 x squared, from 0 to 9, which will give us 81/4. Okay, thank you. Okay, so let's look at the example. So volume at the graph x equals y squared with the triangle cross section. So we'll have a cross section that will look like a triangle, where height is 1/4, and the base is from y equals 0 to y equals 3. So since we're given the base in terms of y, we want to change our equation in terms of y too. So we'll have y equals square root of x. Okay, so let's draw our graph. Y equals root x. So our y, this is our x, so this is our graph of y equals root x. And when we cut this graph, we get a cross section that looks like a triangle. Okay, so this half of the triangle, this part from here to here, will be square root of x. Similarly on this side, square root of x. When we combine the two sides, we'll get 2 root x. Okay, so that will be our base. Our height is 1/4. And since we're doing in terms of y now, we're going to find our integral from 0 to x equals, so we'll plug in 3 for y, so we'll have 3 times 3 will be 9, so 2x equals 9. Okay, so let's do it step by step. Step number 1, draw a picture. Step number 2, take a segment, which is our triangle. We already took a segment. Step number also have to do the points. So we will have our points from x, negative root x. So some point x, since we're on the x-axis, to negative root x, and then we will have the same thing, x to positive root x, because we'll go to this side of the curve. Okay. Step number 3, our area, which will be of a triangle of our cross section, which will be 1/2 base times height. So 1 over 4, 2 root x, and then 2 root x dx. So we cancel this 2 with this 2, 4 with 2, and we get 1/2 of x. Square root of x times square root of x, sorry, can't see it. So square root of x times square root of x is 1/2 x. Okay. And since we found the area, step number 4 will be find the volume and integrate. So as we already said, we're going to have from 0 to 9, since we had our y in terms of 3, so now plug it in, we get 9. So 0 to 9, our area, which will be 1/2 x dx. Okay, and this is a very simple integral to evaluate. We take 1/2 out, get 1/2 times 1/2 x squared, which will be 1/4 x squared from 0 to 9, which will be equal to, when we plug in 9, 81 over 4. Okay.
When using double integrals to solve for area, it is important to know that there are 3 different kinds that you can solve for. Type 1 are areas bounded by a constant function on the right and the left. Type 2 are areas bounded by a constant function on the top and the bottom. And type 3 are areas bounded by variable functions on all sides. Note, for type 1 and type 2 functions, the limits on the second integration are constant. So you can see that both on type 1 and type 2 that the integrals go from a to b, which are constants. And when solving for type 3, we have to break the area into 2 partitions of case 1 and case 2, find the area, and total them up. Okay, so I'm starting with, for my first example, we're going to be solving for a pretty easy equation, y equals x squared from 0 to 2. And if you notice, I will have both type 1 and type 2 double integrals, and that's because when you can solve for both type 1 and type 2 integrals over here, the only real difference is that for type 1 integrals, it's in terms of x, and type 2 integrals are in terms of y, which is why over here I changed it to in terms of y, so x equals the square root of y. So for type 1 integrals, we see that from 0 to 2, and then we move in the y direction. And so when we go up, first we pass through 0, and as we go up, we hit x squared. And for type 2, we are going from right to left. So when we do that, we first hit the square root of y, and then we hit 2. And we're going from 0 to 4, as you can see, from 0 to 4. So when you solve the integral, you see that either way that you do it, you get the same answer, 8/3. For my second example, I'm using an equation that's a little bit trickier, y equals inverse sine of x from 0 to 1. I'm not actually going to be solving this example, but I wanted to show that if you do it in one way, it makes the integral a little bit easier than doing it in the other way. Okay, so for type 1, we would be going from 0 to 1, and we go this way in the y direction, so we first hit 0, and then we hit the inverse sine of x. And as you know, the inverse sine of x is a little tricky to solve for, so let's just show it in the other way. So for type 2, we would be going from, we would be solving from 0 to pi over 2. And as we move from left to right, first we hit sine of y, and then we hit 1. And you can see that this would be a little bit easier to solve for. But as I proved before, either way that you did it, you would get the same solution. Okay, so my third example is a type 3 double integral, and the two equations that I chose were y equals the inverse sine of x and y equals x from 0 to 1. So I'm going to move it down so that you can see the integrals that I wrote. So first I graphed it, and so I'm doing it in both the y direction and the x direction to show that integrating it in one way is easier than integrating it in the other way sometimes. So for the y direction, we would be solving from the bound 0 to 1. And as we move from the bottom to the top, first we hit y equals x, and then we hit the inverse sine of x. And as we see, the inverse sine of x is in this integral, and that makes it a little difficult to solve for. And so let's show it in the x direction. So for the x direction, when we move from right to left, we notice that below 1, the bound on the right is different from the bound on the right when it's above 1. So we actually break it into two separate functions. Sorry, that line isn't quite straight. And so that's what this is. So the top function, or the bottom function, sorry, as we move, so that would be from the bounds 1 to 0, or 0 to 1, I guess. And then as we move from left to right, first we hit the inverse sine of x, which as we change into terms of y is sine of y. And then we hit y equals x, and in terms of y, that would just be y. And then, so for the top part of the area, it would be from 1 to the inverse sine of 1. And as we move from left to right, first we hit sine y, and then we hit 1. So as you can see, sine y is easier to integrate than inverse sine of x, and so we would just do the integrals of both of them and then add them up.
Lastly, we're going to show how we can use double integrals to solve for volume.
So the volume of a solid equals the area of its base times height. So for the base, we would just solve using double integrals. And for the height, if it's constant, then we would just multiply it by the area of the base and we would have the volume. But if it's not constant, which is what we'll be solving for, first we have to imagine that the function that represents height is defined with two variables, x and y, which is what we're going to assume it is. And second, that we have to compress the height onto the base so that it's easier for us to draw a picture and picture it. And next we have to decide on an order of integration, deciding whether we're going to do it in terms of x or in terms of y. And then lastly, we get to solve using double integrals. Alright, so this is an example of finding the volume using double integrals. So here we're going to be finding the volume of a solid between the two functions y equals x squared and y equals x, and they give us a height of x plus 2y. And so we see that the height is in terms of x and y, and since they already give us a height, we don't have to compress it. So next we have to decide on an order of integration, and I decided to do it in terms of x. So we start moving in, okay, so it's from 0 to 1. So we start moving from the bottom and we hit y equals x squared first. And then we hit y equals x. And we have the height and our dy dx. And so first we integrate our height and we get xy plus y squared from x squared to x, and then we substitute in the bounds, and if we simplify it, we get to here. And then next we take the integration and then we substitute in the bounds, and our answer that we get is 13/60.